Matthew Rudd. I'm writing the book Regression, A Friendly Guide, as you can see on screen. This is a new meet for Manning. I'm going to go through a case study that is a nice example for linear regression and logistic regression. These are two of the topics in the first few chapters of my book. And what I'm going to do is I'm going to go through a Jupyter notebook. We're going to go through an example, a case study that's based on a paper from the Proceedings in the National Academy of Sciences. And that paper is right here. The paper is about extinction risks and how they depend on the size of different animals, all vertebrates. Okay, so here's an article from 4 years ago, basically, on extinction risks from this well-known journal, famous journal, top-notch journal. And we're going to go through and we're going to reproduce some of their results. So in particular, we're going to talk about extinction risks for cartilaginous fish. So cartilaginous fish include things like sharks, stingrays, skates, ghost sharks. So we'll see if we can reproduce one of their pictures in particular. Let me show it to you real fast. It's down here. I'm going to try to refrain from switching between tabs too much. But here is one picture. So if you can see in this top picture under models, there we go, we are going to reproduce this purple dotted curve right there, this extinction risk curve for cartilaginous fish. So this paper covers lots of classes of vertebrates, not just fish, not just these kinds of fish. But we're only going to pick this one part, and we're going to reproduce that curve and talk about how to assess that curve. That's the goal. So the overall goal for this case study is to talk about diagnostics for regression. So the coefficient of determination for linear regression, what it means, what it doesn't mean, and then versions of that for logistic regression and binary classification for logistic regression. All right, so and all of this is in my Github repo for my book. The link is right there at the top of this this notebook. And if you want to see, my GitHub name is mbrudd. The repo's name is just regression, so mbrudd/regression. There it is. All right, so this notebook is in that Twitch directory right there. So you can access this later at your convenience and go through it. And if you have any questions about it, please feel free to email me. There's my email address right there, mbrudd@sewanee.edu, because I teach math and statistics here at Sewanee in Tennessee. All right, so let's get into it. The top part of this notebook is sort of standard stuff, libraries we need, modules, things we're going to import. I turned off warnings so that matplotlib won't yell at me. And then the figure sizes are set. They look okay. Like I said, if the text is too small or anything, please let me know in the chat. But the first thing to do is we got to get the data. So to reproduce this model from that paper, we need the data. And this is all about, we're going to study fish. And there's a standard database for fish called FishBase. And if you look at that website, fishbase.org, you'll see a website looks like it's from the late 90s. It's kind of hard to navigate. If you try to get the data from that site directly, it's not so easy. But the people at rOpenSci have made this data available in an R package called rFishBase. There's a link there, and I used that package to get this CSV, to make this CSV. And if we read it in, you see right there, there are 34,000 some odd fish and 101 columns. So you've got a bunch of fish, a bunch of variables, species, genus, pick preferred name M, I don't know what that is, emblematic, don't know what that is. But all we actually want from this data set are the species, the length, and the weight. So these are going to give us the characteristic lengths and weights of the fish. And the lengths are in centimeters, weights are in grams. All right, so if we scroll down here, you'll see some of the fish, the first few of them, and you'll already notice that a lot of the weights are missing, right? These missing elements, we got to deal with that. And the goal here is to estimate extinction risk for cartilaginous fish based on their weights. All right, so we need these weights. So our first order of business is to fill in the missing weights that we need, and we're going to use linear regression to do that. That's called data imputation, and it just happens that in this case, linear regression is totally the right tool for that job. Data imputation is a hard thing to do in general. It can be tricky. You might want to replace things with just the average of a variable. That doesn't always work very well, but in this case, as we're going to see, linear regression does a great job of imputing the missing weights. All right, but to get there, we're going to drop the things that are missing, build our model, and use it to make predictions. So we're going to drop DNAs, and notice there are 34,000 rows initially. After dropping the rows of missing data, we're down to 2,000 some odd rows, so we lose a lot of data there. And so there are a ton of missing weights, right? Once you've got this data, so now I have complete observations, the first thing to do whenever you're going to do linear regression is plot the data. That's always the first step. In fact, with any data analysis problem, data science problem, the first step usually is to visualize your data somehow. Okay, so we're going to look at a scatter plot. And if you look at a scatter plot, we have here, that is not a good candidate for linear regression, right? So if you just plot the weights versus the lengths, notice that on the scale on the y-axis, there's numbers multiplied by 10 to the 7th. So the scale there is 10 millions, right? These in grams. And then the lengths go from, around of order 1,000. Okay, so there's a big difference in orders of magnitude there. And whenever you see that sort of difference in orders of magnitude, you want to use logarithms to deal with it. So the next step is don't look at weights and lengths directly. We want to look at how their logarithms are related. So we take the logs, and to do that simply, I just add these two columns to the data set. So we take the log of the length, the log of the weight. We use those new variables, transformed variables, and when you plot those, you get the perfect candidate for linear regression. That's exactly what you want to see if you're going to do linear regression. We have a cloud of points clustered around a straight line that goes up and to the right. You can see that. And linear regression is going to find the line that fits that data the best. Okay, so already from the scatter plot, you can see this is a good candidate for linear regression. The points follow a line really nicely. So the first step is looking at a scatter plot, right? That's step one. The second step in this kind of problem is to look at the correlation, actually quantify and measure the strength of that relationship. And so the correlation is going to measure basically how much of the data is where in terms of those 4 quadrants you see on the screen there. So the 4 quadrants are upper right, upper left, bottom right. Most of these points are in the upper right and bottom left. That means as the log of the length increases, so does the log of the weight. We have what's called a positive association, and the correlation is going to be positive. If they were mostly in the upper left and bottom right, you have a negative correlation. If they're all over the place, you have a correlation close to 0. Right? So I'm not going to go over the exact formula here, but if you compute the correlation, which is right down here, the correlation turns out to be 0.923. Okay, that's a super strong correlation. Correlations are always between -1 and +1. You never get -1 or +1 in real life, but you also rarely get correlations this strong with real data. This is particular to this kind of data with these biological measurements. The logs are often related this way. But that's a really strong correlation. In lots of data sets, you have correlations of between 0.3 and 0.7 in magnitude. It could be negative, but in magnitude, 0.3 to 0.7. And with social science data, a correlation of 0.3 or 0.4 is still pretty strong, right? But here we have a super strong correlation. So there's no doubt that linear regression is appropriate. So we're going to build a linear regression model. And there are lots of ways to do this in Python. I have more of an R background, so I like using the formula interface. And so that's what I use here. So this is using the stats models formula interface. We're going to get just a regular linear regression, log weight as a function of log length. And there's the model. Okay, so we have the coefficients, we have the intercept and the coefficient of log of length. And there's what the model says. The model says the log of the weight is that linear function of the log of the length. That's kind of a weird equation. And it's maybe easier to think about if you exponentiate things. And if you do, you get that the weight is this number, 0.036, times the length to the power 2.68. That's about the length cubed. And so it says that the mass of a fish, the weight of a fish, is proportional to the length cubed, which is what you would expect in terms of the volume of an object, right? So if you take the side length cubed, it makes sense, okay? But that exponent, 2.68, and the coefficient of 0.036, those are more precise, and they're based on this nice data set. All right, so that's the linear regression model. It's going to give us a relationship between length and weight, so we can compute weights or log weights in just a second that we need. All right, so the first thing to do with linear regression is, or if you're thinking of doing linear regression, the first thing to do is to look at a scatter plot. Second thing is if you think you see a linear relationship, look at the correlation. If together they tell you to use linear regression, the next thing you do typically is you assess the model with the coefficient of determination, right? R squared. We're going to talk about that next. So what R squared does is it tells you how well this model does relative to what's called the null model. Okay, so down here you'll see that the null model, so regression's all about, well, it's about various things, but in this case, regression, we're using it to predict things, okay? Now, one thing you could do to predict the weight of a fish is that, you don't know its weight. You could say you're going to predict every unseen fish, its weight is going to be the average of all the known weights, okay? And that's called the null model. Sort of like if you want to predict the height of the next person you see, randomly walking around the city, you would guess the average height of the person, okay? That's the null model. So in this case, you would just guess either a weight of 44,000 grams, 44 kilograms, 45 kilograms. In terms of logs, you'd guess 10.7. Okay, so does this linear regression model do better than that at predicting weights? Well, that's what, again, R squared, the coefficient of determination, does. That's its job. And here is, so I tried to omit too many formulas from this presentation, but this is an important one that I want to use. I want to talk about and I'm going to use it later. The coefficient of determination, again, R squared, is defined this way that you see on screen there. So TSS is the total sum of squares. SSR is the sum of squared residuals. Okay, so the total sum of squares, for every observation, you see how it differs from the average of all the observations. Okay, so for each observation y, you compare it to the average of all the y's, y bar, and you compute the sum of y minus y bar squared. Add them all up. That's the TSS, total sum of squares. The sum of squared residuals it is similar, but now you compare it to the linear regression equation. So you take, for every observation y, you compare it to the predicted value of y hat, you would say, and then you add up the sum of the squares of all those residuals. What that really does is it compares these two models. You've got the null model, you always guess the average, or you've got the regression model, you guess this linear function of the predictor. So the TSS is all about the null model, the SSR is all about the linear regression model, and this compares the two. Okay, so this, TSS minus SSR is the absolute reduction in the sum of the squares. You divide by TSS to get a proportional reduction. So that number there, R squared, really is a percentage. Okay, so the correlation is not a percentage. The correlation is dimensionless. But the coefficient of determination, R squared, is definitely a percentage, and it's often reported that way. And in this case, if you use the formula directly, 1 minus this fraction, SSR over TSS, you could use it directly. These numbers are provided by the trained model, and you get 0.852, 85.2%. Okay, so what that really means is, by using this predictor, the log of the length, you reduce the variability in the predictions by 85.2%. That's the way to think about R squared, this coefficient. One of my pet peeves is that most intro stats books have this sort of catchphrase about R squared, that it's the percentage of variation explained by the model. And I contend that that is a bad thing. That's a bad way to think about this number R squared, because it suggests, or it imbues the model with too much explanatory power. This model may be totally wrong. You don't know about causality. There are all kinds of issues with that sort of phrasing. But the best way to think about the R squared is it's the percentage reduction in variability that you gain by using the predictor instead of ignoring it. Okay, so the line we're fitting does a much better job of prediction. Okay, all right, 85.2%. Okay, so you could compute this number that way. You really shouldn't, because it's already built into the model, and just call it R squared like you would guess. So there's the R squared, 0.852, 85.2%. So the linear regression model does a way better job than the null model, as you would expect from looking at the scatter plot. All right, so that formula, I'm going to use it again later to talk about how to assess a logistic model. All right, so we now know how the log of the weight of a fish is related to the log of its length, or we could relate the weight to the length by this power law relationship. Now let's talk about cartilaginous fish. All right, so for cartilaginous fish, again, sharks, rays, skates, sawfish, ghost sharks, we're going to get all those fish and their extinction risk classifications from the IUCN Red List, and you can follow the link to see that. So I took that data, put it in this CSV, chondrichthyes.csv, and if you read it, here's what you get. So here are 10 of the sharks, 10 of the cartilaginous fish. I'm going to call them sharks for simplicity, but they're not all sharks. So there are 10 of them, and you can see that from the red list, you get this category. Is the fish near threatened? Is it vulnerable? Is it of least concern? Is it endangered? All these different categories. And we're going to convert that category into a binary response variable in just a second. And then we can do logistic regression. But first, we're going to take this data set, join it with our fish data, get rid of the missing data, and so on. So this next little bit is just sort of some data cleaning. So we'll take sharks and join it with the fish data set, get our lengths and weights in there. So now we have, for these sharks, these cartilaginous fish, we have the species, the extinction category, or the risk category. We have the length and the weight. Notice that the weights are missing, some of the weights are missing, and we have to fix that first. So there we've got our data set with some missing weights. I'm going to get rid of the ones with missing lengths, because our model is for imputing the weights. Okay, so we're going to get rid of the ones with missing lengths, and get rid of the ones for which the category is data deficient. And now we have the data set we're going to work with. All right, so we went from, what did it say? 1,200 rows, 1,200 sharks, basically, to 809. Did it say? Yeah, 809 rows. All right, so now we have our data set. The next thing we'll do is we'll use our linear regression model to fill in those NaNs, not numbers. And again, this is called data imputation, so we're going to add stuff in. Sort of the opposite of amputation, we take things out. So we're going to impute the missing elements. And that formula right there, in that cell, is exactly the power law relationship from before with the parameters from the fitted model. And once you do that, you get these weights. And you can tell which ones have been imputed because they have these nice, they have they're not the nice numbers. They're like 590,000. They're the more complicated numbers. Okay. All right, so now we have weights for all of these sharks. And we want to use the logs of lengths and weights, so we'll add those back in to this data set, and then look at a scatter plot. And here's what you get. So here are the logged weights of the sharks versus the logged lengths. And you can tell, again, which ones have been imputed because they're right on the regression line. One question you might have is, have I committed extrapolation here? Because you can see that the line extends past the points that weren't on the line, but actually no, because the data used to train the model includes lengths outside this range here. So we haven't used any lengths that weren't in the data set to begin with. Okay, so we have not extrapolated, which is can be a concern. All right, so now we have all the weights we need. There's our sharks data set. I don't know why I printed that again. But what we're going to do next is take this category and convert it into a binary predictor, a binary response variable rather. And so these are the threatened categories: critically endangered, endangered, or vulnerable. So if the category value, that level, is one of those three, we're going to count the shark as being threatened. Otherwise, not. Okay, so that's what we did here. So we're going to make this threatened column of zeros and ones. 0 means not threatened. 1 means threatened that is in one of those three categories. All right, so now we're set up for logistic regression. All right, so logistic regression is a way of predicting the probability of an outcome based on some predictor. So we're gonna have a simple logistic model with one predictor, the log of the length, or the log of the weight rather, and then this threatened category. All right, so there's still this, what we're still doing is comparing a null model to a statistical model. The null model in this case is the same as before, really. The null model takes the average of that threatened category and uses that for all future predictions, right? Now, in this case, the average of threatened is the empirical probability of being threatened. It's as you can see here, it's 34.6%. Our null model would say, we think there's a 34.6% chance that any randomly chosen fish is threatened, okay? And you could convert that via a classifier, but that's the null model, okay? This one constant probability for all fish, all right? it's probably not as good as actually using the predictor, the log of the weight. So let's see how that model does. All right, so the sharks model, here we have our logistic model. So we use stats models. Again, the formula interface, threatened is our response, log of weight is our predictor. It's a binomial logistical regression. And here are the parameters that we get out of it. So in my book, if you want to see the details of how this model is fitted to the data, I explain all that in detail, but this is not really the place for that. But here's what you get as for the parameters, the coefficients. And here are two versions of the model. The first says the log of the odds of being threatened is, again, negative 3-point change plus 0.29 times the log of the weight. If you exponentiate and convert that to a power law, like we did before, you find that the odds of being threatened is proportional to the weight to a power. Okay, that's kind of a weird formula. And remember, the odds of something and the probability of something are different. The odds equals the probability over 1 minus probability. But this just says that the odds increase as the weight increases. So bigger fish are more likely to be threatened. That's what that model really tells us. That's the takeaway here. All right. So we have the model. The question now is it any good? Right. So now we'll talk about assessment. And assessment has various pieces here. We could talk about sort of the first stage of assessment. For that, we'll use the likelihood ratio statistic and the deviance. I'll explain that in a second. And then going past that, you have various things you can do. I'll talk about two kinds of things you can do. All right, so there's our model. And for linear regression models, you talk a lot about sums of squares. With OLS models, you talk about sums of squares. Sums of squares based on the average, sums of squares based on the regression model. In logistic models, what you have instead is called the deviance. Deviance is minus 2 times the log of the likelihood, right? The likelihood is a measure of the overall probability of your observations based on your model. I'll stop there for right now. But the deviance is sort of the analogous thing to the sum of squares in linear regression. And what happens when you fit the model is you find coefficients that minimize this number of the deviance. Okay, so you have these two models, these two competing models. They're nested, they're in this hierarchy, however you want to say it. So the null model is just the average, the baseline probability. You've got your logistic model. All right, so when you compare these two models, each model has a deviance, and the likelihood ratio statistic compares them. It just subtracts the what's called the residual deviance from the null deviance. Okay, so that number is again called the likelihood ratio statistic. In fact, there it is, the 60.16 and change. You just take the difference. That's the number you want to look at. It doesn't have an easy interpretation. It's clearly not a percentage. Like R squared with linear regression has a nice interpretation. This one doesn't, all right? But what you do is you just gauge the size of that number, okay? It's called G squared. Depending on the reference, I call it G squared. So you measure the size of G squared using the fact that it's a chi-square statistic with 1 degree of freedom. That's not an easy thing to explain, but that's what it is. And so down there where it says 1 minus chi-squared CDF, all that's doing is, is this a big chi-square score or a small chi-square score? Well, turns out for this problem, with 1 degree of freedom, it's big, okay? So that's a p-value. It's very small, almost, it's not 0, but close to 0. The takeaway from that is that using this predictor, log of length, is way better than ignoring it. Okay, so it's a much better model than just saying that each fish has, whatever it was, a 34.6% chance of being threatened. All right, so great, looks good. If you just look at the likelihood ratio test, that's what this is right there. Looks great. The p-value is small. Moving right along. And if you look at a plot, looks great. Okay, there's the plot. In fact, that is the plot from the paper that I said we'd reproduce. That's the purple dotted curve right there. Okay, I don't know if you can see my cursor there, but the purple dotted line on the models pane panel, we just got it. Okay, we totally reproduced it. So after 25 minutes of talking and showing you these results, we recover their logistic model. We get the same curve they got. You might notice that I didn't show you a plot of this data until just now. and because if you look at the plot, you can tell there's not really a clear breakdown between, you can't see from this that certain weights correspond to being threatened and certain weights don't, right? They're all jumbled together there in the middle. All right, so the logistic curve is what they got in the paper, but if you look at this plot, the curve looks good, but if you look at the actual data points, things maybe don't seem so good, right? So maybe I should have said if we plot the results, things look pretty good at first. But upon further inspection, you kind of wonder, okay, so now is where assessment comes in. So the paper I mentioned, it stops there. It gets these models, and then it just stops, okay? Now they have other models, other classes of vertebrates, so they were doing a sort of bigger project, but for this one class of vertebrates, this one class of fish, we should question whether the model fits very well. So now there are really two kinds of things you can do with logistic models. A standard thing to do is to construct a binary classifier and then use the ROC curve, the ROC curve. Another thing you can do is talk about analogs of R squared for logistic models. I'm going to talk about both. I'll try to be fast, but not too fast. I'll talk about both. So to construct a binary classifier, the standard simplest thing you can do is look at those probabilities from the model, compare each one to 50%, even odds. And if the probability is higher than 50%, say the fish is threatened. If it's not, it's not threatened. Right? And when you do that, like as you see here are the class labels you get. So based on this 50% threshold, we miss that fish, we miss that fish, and that fish. So for these 10, we get 6 correct and miss 4. All right, so 60% accuracy, but we only have 10 out of 800 some odd fish, right? So who knows? So we need to do more work to figure out how accurate this classifier is. And one way to do that is to look at a cross tabulation of the results. And here I'll show you both of these. So if you cross tabulate the classifications in the model with the actual observed values of this threatened variable, you can see that 561 are labeled correctly. All right, the diagonal upper left and bottom right, but 248 are mislabeled. Okay, so this model misses a lot of fish, and in fact, the classifier says that 211 of the fish that are actually threatened are not threatened, and so this is a good example of when with logistic models you often talk about whether what's more important, sensitivity or specificity. What's worse, a false positive or a false negative. In this case, you have a bunch of false negatives, and that's bad because then you're saying these fish aren't threatened when they are. Okay, so that 211 in the bottom left corner, that's really the most concerning part of this table. And you can see that so having said that, the accuracy rate is about 69%. Okay, so not terrible, but not great. One question here, though, is this 50% threshold the right threshold to use or not? And that usually depends on some sort of expert opinion. But one way to deal with that is to look at this, is to see how the true positive rate and the false positive rate vary together as you vary the threshold. And the ROC curve just shows that to you at a glance. I'll just skip ahead to that picture. So the blue curve there is the ROC curve for this logistic model. So by varying this threshold, from 0% to 100%, you can see how well the model does at classifying. And the area under the curve, the AUC here, is 0.66, which is okay. It's not great. You really want the closer the AUC is to 1, the better your classifiers are doing. All right, and you kind of want an AUC of over 0.7 or so. That's kind of one of the rules of thumb. This one's 0.66. If you just guess randomly, that's the dotted line there, you would have an area of 0.5. So it's not that much better than just random guessing. All right, so the ROC curve suggests this model is not so great. Another way to see that is if we look at analogs of R squared, but tailored to logistic models. All right, so I'm going to talk about So, okay, so in this case, there is no standard version of R squared for a logistic model. There are quite a few contenders. I'll talk about 3 of them. All right, so the top 2 that are shown here are maybe the most well known. So the top one is called McFadden's pseudo R squared. So, like I said earlier, the deviance is the analog of the sum of squares. And so in that formula for R squared, you have 1 minus SSR over TSS. You just replace the SSR and the TSS with the deviances that parallel them. And if you do that, you get this, again, pseudo R squared. It's the proportional reduction of the deviance, okay? And in this case, it's 0.057, not quite 6%, right? So in this case, the deviance is reduced by about 6% by including the log of the weight in there, which is not very good. You could also just use the sums of squares, just use the ones in this model, right? So look at residuals, you've got the predicted probability, you have the null probability, the 0.346, whatever it was. You can just compute sums of squares. And if you do that in the formula for R squared, this one's not named after anybody. It's just, I don't know, sum of squares. So in this case, you get R2, I'll call it R2 sub S, and it's 0.074, okay? So it's about the same magnitude as McFadden's pseudo R squared, and that's always going to happen. So, or if it doesn't, that's definitely a problem, but it should happen. So we get 6% from McFadden's pseudo R squared. We get this 0.07 from the sum of the squares, and then a more recent diagnostic is this thing called the coefficient of discrimination. So Chur proposed this in 2009, and it's based on the common sense that a good model is going to give high probabilities to observed successes, the ones, and low probabilities to the observed failures, the zeros. So one thing you can do is just look at a histogram by category, right? So for this logistic model, for the threatened equals 0, the non-threatened fish, the predicted probabilities are pretty low, centered at 0.4, so they're below 0.5, that's good. But they're also low for the threatened class, and that's not good. So what you would like to see is a peak toward the left for the threatened equals 0, and a peak to the right of 0.5 when threatened is 1, which you don't see here. So this statistic, the coefficient of discrimination rather, is the difference in the averages for the 2 groups. So you can look at the average probability for each group and then take their difference. That is this down here, the 0.07. Again, it's not a percentage, but it's 0.08 if you round. So all 3 diagnostics are about the same. And really, if you look at all 3, they should all 3 be about the same. One rule of thumb is that you want them to be over 0.2 or 0.3 or so for a good model, but the higher they are, the better. So all 3 of these diagnostics have the property that for a perfect model, you have 1 as the value, and for a useless model, no better than the null model, you have 0. All right, so after you go through some assessment of this model, you find out, like I said here, it's not very good. So even though we have this paper from a famous top journal, and you can always fit models to your data, depending on the kind of data you've got, you can always fit models. But the question is, should you, or what should you do if the model's not very good? So there you go. So I'm gonna stop here. If you have any questions, post them on the chat. I'll wait for a little bit to see if there are any questions. If you have questions later on, email me. Again, my email address is here at the top. Check out my repo on GitHub. Feel free to fork it and play around with it. I hope you enjoyed it, learned something. Thanks a lot for coming.